Alright everybody, my name is Landon Oubre. I'm a junior in mechanical engineering, and today I'll be giving you guys a run through on the refrigeration cycle. So the refrigeration cycle has four very important steps: compression, condensation, expansion, and evaporation. This cycle is normally used in refrigerators and air conditioners in your home, in your car, etc. The way it works is the compressor gathers low pressure vapor and turns it into high pressure vapor, and it sends it through the condenser, which turns it into a high pressure liquid. That liquid then goes to a capillary tube, which makes it a low pressure liquid, through the evaporator, which returns it back from a low pressure liquid into a low pressure vapor, and then the cycle restarts itself again. So when dealing with the refrigerated cycle, there are two different cycles. There's the ideal cycle and the real cycle. The ideal cycle is more of like it's kind of imaginary. It doesn't really, it's not real. It's not, what's the word? It's not perfect. The ideal cycle it assumes perfect expansion and compression, and it doesn't account for any losses whatsoever. But when it comes to the real cycle, it does account for losses. It does account for the pressure drops to the fluid flows, and it does account for the irreversibilities and heat transfer to the surroundings, to and from the surroundings. So in the first figure, we have pressure versus specific volume. As you can see, it's pretty clear. There's not a lot of interpolation that you have to really do when it comes to the temperature versus entropy. That's when things get a little bit more complex. And then moving on to the pressure versus enthalpy, that's where you have a lot of values where you have to interpolate. So here's our apparatus for the experiment that we'll be doing in the lab. As you can see, there are a lot of complex components associated with this, but the main ones that you really need to be focused on are the condenser, the evaporator, the water reservoir, the compressor, and the expansion valve. So for the first part of the experiment, we're going to go in there and turn on the TRCVC, and then we're going to turn on both of our pumps and set them equal to 5 liters per minute for the flow rate. And then we're going to turn on our compressor, set it to an approximate value of 40%. We're going to allow the system to become steady, and then we're going to record our data. For the second part, there's not much difference. We're just going to do the exact same thing, turn on both of our pumps, activate the evaporator and compressor this time instead of just the compressor. And then for our compressor, we're still going to set it to an approximate value of about 40%. And for the evaporator, we're going to do 3 different flow rates. We're going to do 6 liters per minute, 4.5 liters per minute, and 3 liters per minute. Let our system become steady again, and then record our data. So the data that we want to collect enough to draw the necessary curves for like P to H diagram, T to S diagram, and P to D diagram. We also want to collect enough data to determine the coefficient of performance for refrigeration cycles, and we want to collect enough to determine the heat generation in a condenser. So to determine the coefficient of performance, the equation for that is QL over WC. QL stands for the heat generated for the condenser, and WC stands for the work done by the system. To find QL, we need to do the enthalpy out minus the enthalpy in, and for the work done by the system, we need to do the enthalpy of the second state minus the enthalpy of the first state. To find the heat generated by the evaporator, we have to do the enthalpy of the evaporation out minus the enthalpy of the evaporation in. And to find the power for the system, we need to do our heat generated for the condenser times the mass flow rate. So here are some sample calculations. We're going to assume, using the tables in the thermodynamics textbook for the refrigerant fluid R34A, we're going to assume that the temperature for the evaporator is negative 20 degrees Celsius, and the temperature for the condenser is 40 degrees Celsius. To find the work done by the system, we do enthalpy 2 minus enthalpy 1, which we can obtain from the tables, and to also find the heat from the condenser, we do enthalpy of state 1 minus enthalpy of state 4, which we can also get from the tables. Plugging that in, along with interpolating for state 2 to find the work done by the system, we get 4.23 kilojoules per kilogram. And then to find our heat generated by the condenser, we plug in the values from the tables for state 1 and state 4 enthalpy, and we get 129.6 kilojoules per kilogram. We plug that into the coefficient of performance equation, and we get 3.064. And those are my references.